Okay, hi everyone. Let's go ahead and get started. So today we're going to be continuing our discussion of classification algorithms. So last time we saw the kNN algorithm, and so today we'll see a whole bunch of more details on that method, as well as some more interesting stuff about classification. Okay, just a couple of announcements before we get started. Your homework 1 grades are now available on Gradescope. They'll be up on the Canvas page soon whenever I get a chance to put those in there. The mean score on this homework, if you're curious, was about a 92. So good job, guys. That's pretty good. If you're interested in a regrade request, they are open for 1 week from today. So you have until April 26th to submit a regrade request. If you'd like to submit a regrade request, please do this via Gradescope. Don't post on Ed for these. We can only really do these through Gradescope. And really, you should only be submitting regrade requests if we actually made a mistake while grading your assignment. Unless we, missed your answer to a question or something like that, it's unlikely that we're going to actually, be changing your grade. And please note that we do reserve the right to regrade your entire assignment if you submit a regrade request, which can potentially result in a higher or lower score. So again, these regrade requests are really only there in case, we actually made a mistake while grading your assignment. The second homework is now available on Canvas, so I set an Ed post out to you guys last night with the details about that. This homework is due next Friday, so April 28th, and I encourage you guys to start early on this one. So it's about the same length as homework 1, but maybe a little bit more in the weeds with some of these classification algorithms. And as always, if you have questions on this assignment or anything about the lectures, please feel free to post on our Ed board. For tomorrow's discussion section, the topic is going to be an exploration of the MNIST and Yelp datasets. So this MNIST dataset we saw some examples of in previous lectures. It's this image dataset of handwritten digits. And so you'll see some examples of how you actually work with image datasets in code. And then we'll also be going through this Yelp dataset, which is a text dataset, so a natural language dataset, which you'll be using in homework 2. And so we'll be focusing on those in the discussion, and then there'll probably be some time for sort of Q&A stuff. So come prepared to the discussion section if you have questions on the homework or the lectures or anything about the course. Okay, so in today's lecture, we're going to continue talking about the kNN algorithm. After that, we'll go through sort of a time-space complexity analysis of the classifiers we've seen so far. How do these methods scale with things like data, number of classes, so on and so forth. Then I'll introduce this thing called the curse of dimensionality. So it sounds kind of scary, and it is if you're a machine learning practitioner, but we'll see what this means. And then last, we will briefly go through some ways of comparing the classifiers we've seen so far. So for a quick review of how the kNN algorithm works, what we're going to do first is we're going to fix some number of neighbors, k. So k is some positive integer, 1, 2, so on and so forth. This is some hyperparameter of our model. And then to make a prediction for some unlabeled data point x, what we're going to do is we're first going to find the labels of the k nearest neighbors of that unlabeled data point x in our training data. Okay, what I really mean by this is that we have some distance function d, and we're going to evaluate this distance between this unlabeled data point x and every single feature vector x of I in our training data. So we just compare our testing point and all of the training points. And then we return the labels of the k data points in our training set that have the smallest distance to x. So this is what I mean by finding the k nearest neighbors to x. And then to actually make a prediction for the label for this unlabeled point x, we just return the majority vote of those k nearest neighbors. So for example, if k is 6, and we found that the k nearest neighbors have labels 1, 3, 3, 2, 1, 3, then we're going to predict the label 3 for this new data point x. And if there's ties, which can happen, then we're going to just break those randomly. So flip a coin and pick one of the labels that tied for the majority vote here. Okay, so let's see an example, a little bit more visual of how this algorithm works. So we've got here a binary classification problem. We've got red classes and blue classes. And this is our training data that I have plotted here. Let's say we have some new unlabeled data point x. It's right here in our data space. If we use k equals 1, so we're just looking at the one nearest neighbor to x, the closest training point is this blue point, and then we'll predict blue for this data point x here. If k is equal to 3, we look at the 3 closest data points to x in the training data, and then we count up essentially how many reds and how many blues there are. And in this case, we'll predict red because there's 2 red points and 1 blue point that are closest to x. K equals 5, we kind of expand the radius that we're looking at for this data point x, and we'll still predict red here. Just like in a nearest centroids classifier, you can get decision boundaries for your kNN model. These kNN decision boundaries are piecewise linear, just like the nearest centroid algorithm, but they're going to be much more complex than the nearest centroid classifier. For example, in the nearest centroid classifier, the number of linear pieces of your decision boundary is equal to the number of classes minus 1. So if you have 2 classes, you just get 1 straight line for the decision boundary in nearest centroid. Whereas here for kNN, you can see that even with 2 classes, we get this fairly complex decision boundary here. So kNN is much more flexible than this nearest centroids algorithm. Another comparison between kNN and the nearest centroids algorithm is sort of the number of disjoint decision regions that the model can produce. So in this case, if we add some additional training data, here these red points down here, we can see that the kNN algorithm is able to actually produce 2 disjoint decision regions for the red class. In contrast with nearest centroids, it can only produce 1 decision region per class. So again, kNN is a much more flexible algorithm. Okay, let's look at an example of a sort of real-world data set, and let's apply kNN to this data set. So we've got a wine data set here. It's a pretty popular data set to look at in machine learning. It's a small data set consisting of 178 different wines. So we've got 178 data points. Each of these wines has 13 features about some qualities of these wines, and there's 3 different classes. Don't ask me what the classes are. I'm not a wine drinker, so there's some labels associated with these wines. For our purposes, we're just going to use the first 2 features in this data set. So the first feature is the alcohol content of these wines, and the second feature is how much malic acid is in each of these wines. If you actually want to take a look at this data set for yourself, play around with it, you can load it in just 2 lines using sklearn here. Okay, so let's visualize our data points. This is what they look like, again, just using the first 2 features. The colors of the data points, again, represent the class labels. And we can see here that, doing this classification task is not all that easy. There's a lot of overlap between these blue points and the red points here. And so, fitting a nearest centroid classifier to this data set probably isn't going to work all that well. If we fit a kNN model to this algorithm, what I'm showing here now is the effect of the choice of k, the number of neighbors, on our decision regions. So for k equals 1, we're just looking at the single nearest neighbor to every data point and using that to make a prediction. And the background colors here, this sort of yellow, blue, and purple shades, represent the decision regions of this classifier. So every point in here, some test point gets labeled as yellow, every point in here gets labeled as blue, so on and so forth. And what you can see for small values of k, so here k equals 1 or k equals 5, you get pretty complicated decision boundaries, right? You've got like some weird sharp thing happening up here, and these are pretty complicated. They're still piecewise linear, so every sort of edge here is just a straight line. But if you glue together enough of these linear decision boundaries, you can get some pretty complex decisions. If you increase k a little bit more, so if we make k, say 10 or 40, what you should notice is that these decision regions kind of smooth out. They become a little bit more simple, and they become a little bit sort of more compact. So in essence, this value of k, this number of neighbors, is one way you can kind of control the complexity of your model. So when you hear model complexity, you should think of things like overfitting and underfitting. So for small k, does someone want to venture a guess? Are these models going to overfit, or are they going to underfit to the data? Yeah. Yeah, so the answer is they're going to overfit to your data. For small k, you get really complex decision boundaries. And when you have complex models, they can overfit the training data. In contrast, for large values of k, our model might not be complex enough to really capture the variation in the data. So for example, k equals 40, you can see it's making some errors even on our training data. So this model might be kind of too simple, it might be underfitting our data. In homework 2, you'll be creating pretty similar figures to the ones I'm showing here. And so you'll get to sort of play around with these plots and see how they're actually made. Okay, if you guys have ever heard of these things called Voronoi diagrams, they're very closely related to these kNN algorithms. So this is one of these sort of danger slides. Don't worry about the details of this if you don't follow along. I won't ask you an exam question on this, but it's just sort of good to know for your own enrichment. So these Voronoi diagrams, what they are, is they're sort of a partition of the data space into disjoint regions, which are where each region kind of corresponds to the points closest to some particular given green point. So for example, I might have some green point here, some data point, and this kind of cell surrounding it are all the points on this plane that are closest to this green point compared with all of the other green points. So these Voronoi diagrams really have tons of applications out in the real world, particularly in things like spatial data analysis or computational geometry. So for example, if you're working with some kind of e-commerce data, some kind of maps data, you might be interested in, where's the nearest Starbucks to a particular location in space. These Voronoi diagrams are a nice way of sort of partitioning your space in order to do this. In the case of a kNN algorithm, if you have just one nearest neighbor, so k equals 1, then creating the decision regions for your kNN classifier correspond exactly to creating one of these Voronoi diagrams. One of the cool things about these Voronoi diagrams is they give us a nice way of sort of visualizing and interpreting our decision regions. And as you guys should recall, the choice of distance function we use in our algorithm can have a pretty significant impact on model performance. And so one way of demonstrating the effect of the distance function is looking at these kind of disjoint regions we get out of these Voronoi diagrams. So if in our kNN algorithm we're using an L2 distance, and we partition our input space using this L2 Euclidean distance, which is kind of the standard default choice, you'll get decision regions that look like this left-hand side. And if we change our distance to use an L1 distance, so this is like the absolute distance we saw a little while ago, you can see this has a pretty significant effect on these sort of partitions. And so, it's not sort of intuitively clear just from the formulas how the distance affects predictions, but really this visualization should help make it clear that, this really does have an effect on model performance. Okay, so one thing you might be wondering about the kNN algorithm is how do you actually go ahead and pick a value for k? We saw small k leads to overfitting, large k can lead to underfitting. Sort of intuitively, if k is too small, your predictions can be kind of too noisy. You might have some outlier data point, and if you're only using a single nearest neighbor to make classifications, then these outlier data points can really sort of influence your predictions. So small k leads to kind of noisy predictions, not very robust. If you make k too large, well then you're making predictions based on data points that are potentially very far from the point you want to classify. So if k is something like 100 and you only have 200 data points in your data set, well then you're looking at half of your data to classify just a single point here. And so usually there's some kind of happy medium between very small k values and very large k values where you kind of achieve the optimal error for your model. Again, this value of k is a hyperparameter of the kNN model. It's something we have to choose by hand before actually fitting our algorithm. And just like any other hyperparameter, we can use this sort of train set, validation set paradigm to help us tune the value of k. Okay, so here's a short demonstration of how you actually do this. So on the x-axis in this graph, I have the value of k, the number of neighbors. And on the y-axis here, I have the classification error rate. So this is 1 minus the accuracy of my model. So lower is better for this axis. This is, again, on the wine data that we saw a little while ago. In the red curve here, I'm plotting the error rate on my training data as I vary k. So as you can see, with just one neighbor, I get an error rate of 0. And if I increase k, this error rate slowly increases. But remember that error on our training set is not really what we want to use to evaluate our models, because, we want to evaluate how our model is doing on data it hasn't seen, how well it's going to generalize. So what we do is we also can plot the testing error on our data set. So this is some held out test set, validation set, if you like. And what you can see is this curve has, qualitatively a quite different behavior to it. Rather than just increasing as I increase k, it decreases and then increases again afterwards. And so what this demonstrates to us is that the best value of k that we should pick is here, it's I think 7 or something like this. And this is where the testing error is the lowest. So again, you don't want to pick the value of k that minimizes the training error. You want to pick the value of k that minimizes the testing or validation set error. So one interesting feature of this graph is that you get an error rate of 0% if k is equal to 1 on the training data. So any guesses as to why we were doing so good with k equals 1 here? Yeah. Yeah, exactly. So the answer was, if we're looking at our training data, the point in our training data that's closest to a training data point is just that data point itself. And so of course we're going to make correct predictions on all of our training data if we're using k equals 1. So just kind of a funny feature of kNN that it basically memorizes the training data for k equals 1. Again, you should have this idea of sort of complexity and overfitting and underfitting sort of in your mind as you think about tuning these models. So again, in general, a very complex classifier is going to do really well on your training data, but it's just not going to generalize well to new data we didn't see before. So as we pointed out on the last slide, if k is equal to 1, we just have one nearest neighbor. We'll get perfect memorization of the training data, so we'll get 0 training error. This is a model that's just kind of too complex usually. If k is equal to n, i.e. we look at every single data point in our training set to make predictions, this is kind of the simplest version of a kNN classifier, where we're just going to predict the majority class in our data set. So we'll see a little bit more details on what I mean by that in a little while. Generally, you want to pick some value of k that's probably bigger than 1, but a lot smaller than the total number of data points that you have. And again, choosing k depends on what data set you have and requires a little bit of experimentation to actually decide. So, another graph to keep in mind for all of these kind of model tuning processes is that we can put something like complexity on the x-axis. Here, k, the number of neighbors, kind of captures model complexity. And on the y-axis, we can put essentially the error rate. So generally, as you make the model too simple, the training error rate increases. And what you should see is on your testing data, the testing error rate decreases for a while until it reaches some optimal level of performance, and then eventually will increase again when you start to overfit or underfit. So again, just an illustration of overfitting and underfitting in particular to this kNN model. Okay, so for another example of how kNN does on this MNIST data, so I introduced you guys to this data set in the previous lecture. It's a data set consisting of handwritten digits. It's a pretty classic data set in ML, very widely used. And what I've done here is I've gone ahead and fit a kNN algorithm to MNIST where I vary the values of k. So I'm just going to demonstrate what effect this choice of k has. One sort of caveat here is that I'm only using 10,000 of my data points for training and 1,000 for test. This is because kNN can be kind of slow on very large data sets. So I'm just kind of taking a subset of my data for illustration purposes. One thing you should ask yourself is, what is a good error rate for this classifier? Like, if I get an accuracy of X%, is that good accuracy or bad accuracy? And one really simple baseline that you can keep in mind for sort of like, what's the worst classifier I can come up with, is this so-called like majority classifier. So what I mean by that is that in this MNIST data set, all of my classes occur with equal frequency. So 10% of my data is zeros, 10% of my data is ones, 10% of my data is twos, so on and so forth. All the classes are equally likely to appear in my data. What that means is that, if I write down a really bad, kind of stupid idea for a classifier, like predicting 0 for all of my digits, or just predicting a totally random class for all of my digits, it'll be correct about 10% of the time, which is, a lot better than 0%. But what that means is that a sort of baseline error rate for this data set is something like 90%. So if you're doing worse than 90%, you're probably doing something wrong. And if you're doing a lot better than 90%, you're doing a lot better than this, sort of very, very simple baseline. This baseline error rate can be a lot smaller on different data sets. So for example, if you, say, have a binary classification problem with all classes occurring equally frequently, this baseline error rate is only something like 50%. So my point here is that a good error rate is really sort of contextual based on the data that you have available. Okay, so in this graph, I'm showing you, again, on the x-axis, the number of neighbors, and on the y-axis, the classification error rate. With the nearest centroid algorithm on the MNIST dataset, we got something like a 20% error, but using kNN on this MNIST data, we get something like, 3 to 5% error, which is, a huge boost in performance, just by changing our algorithm. On this data set, it just so happens that k equals 1 gets the best error rate on the testing data. But again, choosing this value of k is highly dependent on the data you have available to you. Okay, so another thing that I'd like to sort of emphasize about the kNN algorithm is that distances in general are very sensitive to the dimensionality of our problem. Again, what I mean by dimensionality is the number of features I have in my data set. So for something like MNIST, I have 28 squared different pixels, each pixel corresponding to a feature. So it's a very high dimensional data set. Both the nearest centroid algorithm and the kNN algorithm rely on distances to make predictions. And these distances can be very sort of unreliable in high dimensional spaces. So for example, we saw previously that if you have features that are not scaled properly, if you have some features that are larger than others, these can really sort of dominate the distance calculations and can lead to poor performance of your model. But another way that distances can be unreliable in these high dimensional spaces is that they can actually be noisy to sort of irrelevant features that are not actually predictive of the label that we're interested in. So for example, maybe in like an e-commerce setting, a website like Amazon might collect thousands and thousands of features about every one of their customers. And they'd like to use those features to predict whether or not someone's going to purchase a particular item. So this is a classification problem. Will they buy this thing or will they not buy this thing? But since we've collected so many features about our shoppers, there's going to be lots of those features that just aren't sort of relevant for making the prediction we care about, And so in general, we kind of have these irrelevant features that just might not be useful for us. But this is kind of a problem for things like the nearest centroid and the kNN algorithm, because these algorithms can't really ignore irrelevant features. If we have these irrelevant features in our data set, they're going to affect our distance calculations. And so, having irrelevant features can often lead to sort of poor performance for these distance-based classifiers. We'll see later some other classifiers like decision trees that are actually quite, robust to these noisy features. They can almost do feature selection where they kind of throw away irrelevant data and just keep the features that are, actually useful for making predictions. So let's just see like an actual demonstration of what effect this has. So again, we're looking at this wine data set. And what I'm doing is on the x-axis, I'm adding additional features to this data set that are just pure noise. So I'm adding extra columns to my data set that are just random numbers, basically. You would think that, if my classifier is good, it should be able to kind of just ignore these random numbers and use kind of the good information in my data set. But what happens for these distance-based classifiers is they can't ignore these irrelevant features. And what happens is the error rates of both kNN and nearest centroid increase as I have sort of these irrelevant features in my data. So This is one of the drawbacks of these distance-based classifiers. They really sort of can't ignore irrelevant information. Here's the same type of plot, but now on the MNIST data, just demonstrating that this isn't just limited to this very simple wine data set. It's kind of a general problem that happens with all distance-based algorithms. Okay, so let's briefly summarize our kNN classifier. The basic sort of properties, things to keep in mind about this model, are that for small values of k, you'll get complex boundaries, often leading to overfitting. For large choices of k, the number of neighbors, you'll get smooth boundaries and can sometimes lead to underfitting. The strengths of this model are that it's fairly simple to implement, and you only have a single hyperparameter to tune, just this k value. And so model selection here can be a fairly straightforward process. And as we saw on the MNIST data, it can be pretty accurate on some problems. Getting an error rate of 4 or 5% on this pretty high dimensional task is no small feat. But of course, it has a couple of weaknesses. The main weakness, really, is that it requires storing all of your training data in order to make predictions. Because to make a prediction, we need to compare the distance from a new data point to each one of our training points. So oftentimes, kNN has pretty high memory and time complexities. And another thing, as we demonstrated, is that it can lose accuracy as we get more and more features. So this is kind of undesirable. We would hope that more data would help us make predictions, but can actually hurt for these kinds of models. Okay, any questions on kNN before we move on to time and space complexities? Yeah. Yeah, so that's essentially the effect I'm showing here in these graphs. As we add more and more features to our data, they might not all be very predictive of the label that we're interested in. They might kind of be irrelevant for our task. And because these models depend on distances, those distances have no way of ignoring those irrelevant features. They play a part in that distance computation. And so as we get more and more features, these models can kind of suffer. Not always, but it can be, especially for very high dimensional problems. So going from 2D to 3D, you probably won't see this effect necessarily, but if you go from 100 dimensions to 10,000 dimensions, like in a very difficult ML problem, then you might start seeing effects like this. Yeah, another question. Yeah, so the question is, what distance do we use in kNN? And the answer is you get to pick. So the default choice is usually Euclidean distance, but I guess it's sort of another hyperparameter that you can tune. You can choose an L1 distance, an absolute distance, and see how your model does. So I don't have the formula in these slides. Go back to the previous lecture and review the formula for this, yeah. Yeah, another question. Mm-hmm. Yeah, so just to reiterate, the question is basically, what do we do if we have a very imbalanced data set where most of our data comes from one class and another smaller proportion comes from a second class? And there's various tricks to handle this, like you can downsample the majority class so that they're balanced, or you can upsample the minority class so that they're balanced. It's a little bit of an advanced topic we don't have time to get into here, but ask me after class and I can give you more details. Cool. So in the interest of time, let's move on to the next part of today's lecture, where we're going to be analyzing the time-space complexity of the classifiers we've seen so far. So just for a little bit of notation here, just to set the stage, We're going to use n to represent the number of examples, either training examples or testing examples. We're going to use d to represent the dimensionality of our problem, so the number of features we have. We'll use c to represent the number of classes. For kNN, k is the number of neighbors. We're going to make the assumption that the number of data points we have is much larger than the number of neighbors we're going to use, and also that the number of data points is much larger than the number of classes we have. Okay, we're going to use big O notation, which I'm assuming most, if not all of you guys have seen before. Essentially tells us how the algorithm scales in the worst case. So if something is O of nd, then it's linear in both the number of data points and the dimension. If we've got something like O of dn squared plus cn, the dominant term here is the sort of quadratic term in n, and so this would be a sort of quadratically scaling algorithm. So we're interested in analyzing both the time complexity and the space complexity of our models, as well as sort of separating these analyses into the training phase of our algorithms and the sort of prediction or deployment phase of our algorithms. Okay, so why do we actually care about this? You know, why should we analyze our training and testing complexity in the first place? And you know, the reason is that in real applications, in practice, your data set size n and your dimensionality d oftentimes can be huge. So n could be on the order of, say, millions of data points, or even sometimes billions of data points nowadays. And you might have something like 100,000 different features in your data set, or even larger. And so, of course, we want to avoid scaling that is, sort of larger than linear. So something that's like quadratic in the data set size is, if it takes you something quadratic in a million data points, it's going to be way too slow to train. It's just never going to actually work in practice. But again, something that's like sort of linear in each dimension is typically fine. And oftentimes for ML algorithms, you'll see something like O of nd for both time and space complexities. We care about time complexity because you might want to train something like 1,000 different models in order to evaluate and tune hyperparameters. You might want to also compare different classifiers. And so it's fairly important that you can train these models in a reasonable amount of time. Another reason you might care about time complexity is you might actually want to regularly retrain your models. So for example, if you get new data kind of coming to you over time, it's useful to keep your models up to date in order to make the best predictions possible. And you care about space complexity, at least during training, because you might be just limited by the amount of data you can store at once. So for example, something like a neural network often is trained on a GPU, and these don't have unlimited memory, and so space complexity is something good to keep in mind. In terms of the prediction phase of our algorithm, so after we've trained our model, we care about the time complexity of predictions because often we want our predictions to be very fast. For example, you might want to have real-time interactions with your ML model in some sort of web-based or interactive environment. Another really good example is in like an autonomous vehicle. If your model takes 5 seconds to decide to brake for a pedestrian in the road, that's obviously not good. So you want your models to be quite fast. And also in terms of space complexity for predictions, you might be deploying these models on some memory-limited devices. So you might be deploying a model on a mobile device or like a Raspberry Pi if you're doing some like, facial recognition thing. So, it's good to keep these sort of costs, both in time and space, in mind. Okay, so let's think about the time-space complexity for our nearest centroid classifier that we've seen. In terms of training this model, for the time complexity, it's O of nd. And the reason it's O of nd is that because to train this model, all we have to do is compute each of the centroids. So we have C centroids that we need to compute, which requires taking an average over all of our n data points. And each of these n data points has a total of d components. So if you just count up all the calculations you need to do to compute those centroids, you'll get something like O of C times nd. And here I'm dropping the C term because it's minuscule compared to the number of data points n, just by assumption. In terms of the space complexity, it's O of nd coming from the data matrix. So we've got n rows and d columns. We've got also a vector of labels, so we've got n of those. And then we've got C times D corresponding to storing our C centroids. So in practice, this is effectively just O of n times D because typically n is much larger than the number of classes C. In terms of prediction, to make a prediction for a single data point x with our model, the time complexity here is going to be O of CD plus C because we need to compute the distance between x from each of our centroids, and computing this distance requires O of D calculations because we have to essentially sum up the distance between each of the components between the data point x and that centroid. So this O of CD is computing the distance between x and the centroids. And lastly, this plus C factor is because we need to then find the minimum distance. So we can do this linearly in the number of classes. And then in terms of the space complexity, all we need to do to actually sort of store our model is save the C centroids, each one having dimensionality D. So the space complexity here is O of C times D. Okay, let's now do the same analysis for our kNN algorithm. So for training, really there's no training that happens with kNN, right? All we do is look up distances between a testing point and all of the training feature vectors. So again, effectively no training cost here. The space complexity for kNN, however, is pretty high. So we need to store n times d numbers, essentially corresponding to our data matrix containing our training data. So we've got n rows and d columns in our training data matrix. We also store a vector of n labels, but we can essentially ignore this because the nd term is going to dominate here. So notice the space complexity here is n times d for kNN, but it's c times d for the nearest centroids classifier. And so, scaling linearly in the data set size is much worse than scaling in the number of classes. Okay, so for the time complexity of the kNN algorithm, just a reminder again of how this works, we need to compute the distance between an unlabeled data point and each of our training points. This again is an order of n times d computation because each distance is order of d steps, again, comparing every single component in our feature vectors. And we do this n times, once for each data point in our training set. Then what we need to do is actually find the k smallest distances in this sort of distance matrix that we calculate. Okay, so the first option for finding the k smallest distances using this algorithm is that we could take all of our n distances between our testing point and our training points, and we could sort them and just take the k smallest values. If you use something like merge sort, for example, this will add a complexity of n log n to your prediction. The second option is we can be a lot smarter about how we actually find these k smallest distances. So one way to do this is that as we compute our n distances, just looping over our training data, we can keep a sorted list of the k smallest distances we have seen so far. Then at every iteration of this loop through the training data, we can check if the current distance is smaller than any of the k distances we have stored in this sort of list of smallest distances. If it is, we can insert that distance and then delete the largest of those k distances. And so this is linear in the number of neighbors k at every iteration of this loop. And we do n iterations of this loop, one for every single training data point. So we'll get O of nk time complexity for this option. Okay, the third option is you can, think back to your data structures class and use something like a heap data structure. So if you're not familiar with heaps, don't worry about it. But it's something like a binary tree that allows you to sort of insert or delete elements from a sorted list of length k and time log k. So we go from a linear sort of insertion deletion step up here to a logarithmic insertion deletion step down here. The basic idea is you can sort of avoid scanning over this list of smallest distances and search using some kind of usually tree-based structure. So don't worry too much about the details of option 3 here. Just know that there's clever ways we can find these smallest k distances. Okay, so overall we have sort of three options for implementing our kNN algorithm, each one leading to a different time complexity during sort of the prediction phase of this model. So each of these we pay a factor of n times d, essentially for computing the distances. And then these additional factors here come from the different options for sort of sorting or searching for the k smallest distances. Okay, so some brief comments here, like which of these options should you actually choose in practice? Option 1 is definitely the easiest one, and for small data sets, so where n is small, then option 1 is totally fine. Options 2 and 3, so comparing sort of this heap data structure to this kind of more clever way of sorting for the k smallest distances, sort of might not be all that significant. We have sort of an nk term versus an n log k term. So if k isn't very large, the number of neighbors isn't very large, options 2 and 3 are going to be pretty similar. And in general, if sort of the dimensionality of your data set is much larger than the number of neighbors, then this first O of nd term is going to dominate in general. One thing to note is we ignored the cost of computing this majority vote at the end of our classifier, but this is a negligible term. It's dominated by the other terms in this analysis. So I know we went a little fast through sort of the description of these. I highly recommend you guys go back through these slides and make sure you understand why each of these time and space complexities is the way it is. Okay, let's look at some examples of what this actually looks like in practice. So I'm looking at my MNIST data set, and on the x-axis, I'm varying the number of training data points n, and on the y-axis, I'm varying the prediction time, i.e. how long it takes to classify a data point, for kNN, depending on how much training data we have. And sort of as promised by those analyses we went through just a minute ago, this is linear in the number of data points. So more data means slower predictions. We can also look at the dependence on D, the number of features. So here I'm essentially throwing away some of the features in my MNIST data to sort of simulate this. For the nearest centroid algorithm, there's linear dependence, as well for the kNN algorithm. But kNN, you can see, scales much worse with the dimensionality of the data. So if you need really fast predictions, maybe you would choose nearest centroids over kNN, even if it has worse performance in terms of sort of accuracy. Again, showing a similar graph here with sort of the linear dependence on the number of neighbors k and sklearn. And of course, you can ignore the red graph here because there's no nearest neighbors in the nearest centroid algorithm. Okay, so any questions on our time-space complexities? For which variable do you mean? So for nearest centroids, the prediction time is C times D. So it is linear in the number of features you have. But as you can see from that previous graph, that sort of constant on that linearity, the slope is not very large. Yeah, other questions on our complexity analysis? Cool. Yeah, so make sure you guys go back and review those calculations. Okay, and with the last few minutes here, I'm going to introduce this idea of the cursive dimensionality, and then we'll skip this last point and save it for Friday's lecture. So in machine learning, there's this kind of colloquial term called the cursive dimensionality. And it really refers to this fact that classifiers relying on distances or kind of density-based arguments generally perform poorly in very high dimensions. So they don't scale well to high-dimensional problems. So we already saw before that if we increase the number of features in our data set, these distance-based methods can have an increased error rates. And here I'm going to give you kind of a heuristic explanation that should help you kind of conceptualize why this is happening. In particular, we're going to be thinking about sort of the density of data points as we increase the dimensionality of our feature space. So again, let's look at our wine data set. Here I've got my data points plotted. And what I'm going to do is I'm going to introduce sort of a toy classifier that doesn't really get used in practice, but is good for sort of illustrating this idea of data point density. So this is called the binning classifier, where what I do is I'm going to bin each of my features into B bins. So I'm essentially just partitioning my data space into sort of a grid. And this defines a B times B grid of sort of cells in my data space here. To define a classifier from this, all I'm going to do is pick the majority class in each cell and make that prediction. So for example, here, I'll predict red if I have a training point or testing point that comes along. Here I'll predict something like blue. So if we sort of fill in the decision regions, it'll look something like this. And of course, we can then get out sort of the decision boundaries. These are going to be along the lines of our bins. If we have a really large number of bins B, we can get quite complex decision boundaries out here. So again, this is just for illustration. People don't really do this binning thing in practice. But what you should notice is that in D dimensions, the number of bins you have is actually B to the D. So it's exponential in the dimensionality of our feature space. So, for example, even with, say, 10 bins for each feature, B equals 10, if D is very large, we have lots of features, we're going to have lots and lots of bins. Okay, so again, just to reiterate how this binning classifier works, to train it, we just compute the majority class in each of our B to the D cells, and then store this as some D-dimensional array corresponding to the prediction in that bin. And then prediction just corresponds to looking up which of these cells a data point X belongs to and predicting that label. But again, the number of these cells is growing exponentially with the dimensionality of the data. So even with 10 bins, so pretty small number of bins on each axis, even for something like 20 features, we've got 10 to the 20 different cells here. This is something on the order of like 1 million. For something like, say, 40 features, D equals 40, we'll have something like 1 billion different cells. So the first problem you run into in high-dimensional problems with lots of features is just memory costs. So if we have 1 billion different cells, that requires storing 1 billion different sort of labels for each of our cells, and it's not something we can actually do in practice. But the second problem we'll run into, and this is this kind of density thing that I'm trying to emphasize here, is that most of your cells are going to have no data points in them. So even if we have 40 features, so 1 billion different cells, if we have a huge data set with 1 million data points, in this fairly low dimensional feature space, only 40 different features, about 1/1,000,000th of the cells have no data in them. We just have so much more space in these high dimensional spaces than we have data to sort of possibly fill them out. So, unless we really have, an absurdly massive data set, we just kind of don't have enough data to really explore the data space sort of in an efficient way. And this is really what I mean by the curse of dimensionality. For very high dimensional problems, there's so much space in our sort of data space, because again, it grows exponentially in the number of dimensions. So things like distance-based methods, are particularly sensitive to this issue of just kind of having sparse data. Okay, so in the interest of time, we're going to skip ahead, just wrap up quickly. So today we talked about the kNN algorithm again. So we've completed our discussion about this algorithm. Again, keep in mind the number of neighbors k is a hyperparameter that you should be tuning on a validation set. It can really affect the performance of your model. We then went through some classifier time-space complexities, and in Friday's lecture, we'll see some comparisons between various methods using the analysis we did here. But in general, it's important to consider how your model scales in terms of the number of data points you have, the number of features, the number of classes, so on and so forth. And lastly, I introduced this kind of conceptual idea of the curse of dimensionality, where really the space in your sort of data space is growing exponentially with the number of features.